Hello, everyone. Today, we will discuss Section 3 of Chapter 4, BFT Consensus Algorithms. The most important aspect of BFT consensus algorithms is Byzantine fault tolerance, BFT. Byzantine fault tolerance is a type of fault-tolerant technology used in distributed computing, where the Byzantine general's problem is the main challenge that many algorithms aim to solve. The algorithms designed to address this issue are collectively known as Byzantine fault tolerance, BFT, algorithms. BFT has been studied since the 1980s and is now a well-researched theory. In distributed computing, there are two definitions related to Byzantine faults and failures. The first is Byzantine fault, meaning that a fault manifests different symptoms depending on the observer's perspective. The second is Byzantine failure, which occurs when Byzantine faults lead to the loss of system services in a consensus-required system. In a Byzantine system with multiple nodes, a Byzantine fault-tolerant system needs to ensure that for every request issued by each node, the following two conditions are met. 1. All non-Byzantine nodes use the same input information and generate the same result. 2. If the input information is correct, all non-Byzantine nodes must be able to accept the message and compute the corresponding result. The common assumptions used in Byzantine systems include: the behavior of Byzantine nodes can be arbitrary. Byzantine nodes can collude. Failures between nodes are independent. There is unreliable network communication between nodes, meaning messages might be lost, arrive out of order, or even be corrupted. However, most protocols assume that messages will be transmitted within a finite time and eventually reach their destination. Moreover, messages exchanged between servers can be known by third parties but cannot be tampered with, including message forgery and ensuring message integrity. Most classical distributed consensus mechanisms use Byzantine fault tolerance techniques. We can classify classical distributed consensus mechanisms into three categories based on the network model. 1. Synchronous network distributed consensus algorithms, where the network model assumes that all communication happens within a known time frame. This assumption can be overly restrictive in practical applications and may lead to problems. 2. Partially synchronous network distributed consensus algorithms, which are the most commonly used network assumptions in both classical consensus mechanisms and blockchain systems. This category includes the previously mentioned practical Byzantine fault tolerance, PBFT, mechanism and several of its improved versions. 3. Asynchronous network distributed consensus algorithms, where consensus mechanisms are implemented in a completely asynchronous network, usually requiring random number generators to function. It's worth noting that the Byzantine fault tolerance mechanism was proposed by two scholars from MIT in their 1999 academic paper titled Practical Byzantine Fault Tolerance. This method builds upon prior work and optimizes it, making it widely applicable today. PBFT reduces the operational complexity of Byzantine protocols, lowering it from an exponential level to a polynomial one, making Byzantine protocols feasible for distributed systems. The PBFT mechanism is a new state machine replication algorithm that provides both liveness and safety in the N+3F+1 model. In the PBFT consensus mechanism, there are two types of nodes: the primary node and the backup nodes. The primary node's main responsibilities include accepting transaction requests from clients, verifying the client's identity, assigning a request number, and broadcasting the preparation message when the system is operating normally. When the node is elected as the primary node, It sends new view information based on the collected view change messages, allowing other nodes to synchronize the data. The primary node also works with all the other backup nodes to maintain the system's operations. Backup nodes are primarily responsible for forwarding messages and voting during the consensus process. The primary and backup nodes can transition between each other. The PBFT consensus mechanism consists of two parts: distributed consensus and view change. In PBFT's distributed consensus, consensus is achieved through three phases: the pre-prepare phase, the prepare phase, and the commit phase. The view change protocol ensures system liveness by allowing the system to elect a new primary node if the current primary node fails. At the same time, to ensure safety, PBFT introduces a checkpointing mechanism where each message is associated with a sequence number. Once a message is completed, its sequence number becomes the current stable checkpoint. In PBFT, each view corresponds to a primary node, and the primary node is elected in turn, with backup nodes associated with it. Other types of BFT consensus mechanisms include Hot Stuff, SBFT, Honey Badger BFT, and so on. Alright, everyone, that concludes the content for Section 3 of Chapter 4.